So today I'm going to be going over some limits, and I'm going to be going over some derivatives as far as the product rule and the quotient rule, how they apply to derivatives and how important they are, obviously. We'll start with limits. So you should have already learned a decent amount of limits. I'm gonna first start looking at limits from a numerical approach. So basically, when you have a function, let's say, f of x equals x plus 1. It's a pretty straightforward function. It's pretty obvious that when we, input 1 for x, the function will be equal to 2. Input -1 for x, the function will be equal to 0. So on and so forth. Very straightforward function. But what we're interested in is how limits are concerned with this function. So for example, if you put in values for x, as those values get closer and closer to a particular x that we're looking for, the limit, what does the output of the function of x look like? So for a very straightforward example, we'll look at x approaching 2. So we'll have the limit as x approaches 2. Now something very important to limits is we can find values very close to 2 that are both above 2 or greater than 2, or values that are close to 2 that are less than 2. Usually in a limit, we'll think of that as the limit as x approaches 2 from the left hand, which we denote with a little minus sign, and the limit as x approaches 2 from values greater than 2, which we denote with a little plus right there. So the best way to picture this is to think of your typical line graph. Just, if we have a line where 0 is basically the origin right here, any values over here are negative, any values over here are positive. But if we instead just look at the point 2, basically what we can say is any point over here is greater than 2 and any point over here is less than 2. So that makes the minus and the plus make a little bit more sense there. Alright, so let's just take one of these for example to start with. So the limit as x approaches 2 from values greater than 2. So we'll denote the limit as x approaches 2 with the plus. So what are some values that are close to 2 but aren't 2 that are greater than 2? So something pretty big and simple, straightforward. We'll just say 2.5. So we'll choose x to be 2.5. It's obviously greater than 2, but it's not 2. So then we'll go ahead and just evaluate this function when x is 2.5. So function, function of x equals x plus 1. So a function of 2.5 equals 2.5 plus 1. 2.5 plus 1 is 3.5. Pretty straightforward. But the thing we want to note is what happens when this value that we're plugging into the function gets closer and closer to the limit, which in this case is 2. So we want to pick a number less than 2.5 but greater than 2. So we'll go ahead and put 2.1 in. And that'll give us 2.1 plus 1 equals 3.1. So it's kind of getting pretty obvious at this point that the limit as x approaches 2 from the values greater than 2 is 3. But we'll put in one more value just to be sure. So something that's very close to 2 but not 2 and is greater than 2 is 2.0001. So we'll go ahead and put that into our function. Oops. There we go. 1 equals 3.0001. So it's very obviously getting closer to 3. So we would say that, let's see, I'll scroll down a little bit here. So we would say that, so for our function f of x equals x plus 1, the limit as x approaches 2 of x plus 1 equals 3. And then we'll go ahead and do the same thing for the left-hand side of 2. So for values less than 2, but close to 2, we can evaluate a couple values of a function. So we'll go ahead and, a number less than 2, but still close to 2. Very simple example is 1.5. So we put 1.5 into our function, and we'll get 1.5 plus 1 equals 2.5. And we'll take a value a little bit closer to 2. Function of 1.9 equals 1.9 plus 1, which equals 2.9. And so on and so forth. We'll keep going. 1.999. Function of 1.999 is 1.999 plus 1, which equals 2.999. So pretty obvious in this example, but you got to start somewhere. So as the limit as x approaches 2 from the left-hand side of x plus 1 equals 3. So in this case, we see that as values approach 2 from both values greater than 2 and values less than 2, they kind of converge to the same number, which is 3. So, the limit from the upper bound of x is 3. The limit from the lower bound of the function as it approaches 2 is 3. So we can actually conclude that the entire limit as x approaches 2 for the function of x equals 3. And that's actually a pretty important definition you'll find out, especially when we look at the like a graphical approach to limits, is that for the limit, to find the limit has to be the same for values less than 2 or less than the limit and greater than the limit. So in this case, the limit as x approaches 2 from the left-hand side of the function of x is actually equivalent to the limit as x approaches 2 from the right-hand side. And since this is true, we can conclude that the limit, which we found to be 3 in each case, of x as it approaches 2 is actually equal to 3. 3. There we go. All right. That's a pretty basic gist of limits. Let's go on to something a little bit more complicated. So let's say we have a function. So f of x equals x plus 2 over x minus 3. And let's say we want to find the limit as x approaches 3. So one thing with limits is if you can just evaluate it at the limit, it's usually easiest to do so. Like in the previous example when we had the function of x equals x plus 1, and you want to find the limit as it approaches 2, well, the evaluation of 2 in the function of x would be just 2 plus 1, which is 3, which is what we found our limit to be. But in this case, when we evaluate 3 in our function, so the limit as x approaches 3 for our function x plus 2 over x minus 3, so I'll plug 3 in the top, we'll get 3 plus 2, and in the denominator we actually get 3 minus 3, which is 0. And the issue with this, obviously, is that division by 0, that's undefined. Division by 0. So you might look at this and say, oh, well, we can't divide by 0, so the limit doesn't exist. And that's definitely a thing, is that sometimes limits don't actually exist. But there's actually some tricks to this. We'll find as we put in values that are close to 3 but not 3, that are greater than 3 or less than 3. So let's start with values greater than 3. So we have our function, which is x plus 2 over x minus 3. We're going to find the limit as x approaches 3 from the right-hand side. So we'll start plugging in values that are close to 3 but greater than 3. So again, we'll start with something pretty simple, something obviously greater than 3, 3.5. So we plug 3.5 into our function. Let's see, the numerator will be 3.5 plus 2, and our denominator will be 3.5 minus 3, which simplifies to 5.5 over 0.5. So I'll basically just double the numerator to get a whole number, which is 9. Okay, that doesn't seem like it would be the limit, so we'll go ahead and do it again with a value a little bit closer to 3, but still greater than 3. So we'll go 3.1. So if we evaluate the function of x at 3.1, so we'll find the limit as x approaches 3 from the positive side. F of x would be 3.1 plus 2 over 3.1 minus 3. Go ahead and simplify this out. We get 5.1 over 0.1, and multiply that numerator by 10 to get a whole number. We get 51. It's kind of strange. You'd think how it goes from, when we evaluate at 3.5, it goes up to 9. When we evaluate at a lower number, it evaluates higher. That's actually because as we get closer and closer to 3 from the positive side, we're making the numerator smaller and smaller. So if we were to evaluate it again, for example, at 3.001, we'll find that basically the numerator will relatively stay the same. 5.5 is not too much different than 5.1, but the denominator will get increasingly small, very, very close to 0, which basically means that our actual number, our whole number, our limit, will just get greater and greater. So when we evaluate this, it'd be 5001. So we can kind of conclude from this, if we have the limit as x approaches 3 from the positive side of the function of x, which is x plus 2 over x minus 3, it actually goes to infinity. So as we keep on getting values closer and closer to 3, we'll just get basically an infinite number for our limit. So we'll know that this is our final limit if we go ahead and evaluate a couple of values or find the limit as x approaches 3 from values less than 3. So let's go ahead and do that now. Let's go ahead and do the limit as x approaches 3 from the left-hand side of the function of x. So last time we picked 3.5, so this time we'll just pick 2.5. So we'll evaluate x at 2.5, so we'll get the limit as x approaches 3 from the left-hand side of 2.5 plus 2 over 2.5 minus 3. And then we go ahead and do that arithmetic. We get 4.5 over, negative 0.5. Okay, so this one is negative 9. Our previous one was just 9. This one's -9. So we'll go ahead and do it again. We'll evaluate. Let's see, 2.9 is a little bit closer to 3 than 2.5. So we'll go ahead and do the limit as x approaches 3 from the left-hand side of 2.9 plus 2. Go ahead and do that over 2.9 minus 3. And that is 4.9 over -0.1, which is -49. So you'll see that this one, this limit is actually getting closer and closer to -infinity. So now we have a function whose limit is positive infinity from one side and negative infinity from another. And if you remember our previous definition, the limit only exists if it's equal on both sides. So it'll make a lot more sense when we look at it graphically, but from a numeric perspective, obviously, since we have one limit that's infinite and another limit that's negative infinite, the limit actually we would say does not exist, so DNE. All right. Then we'll go ahead and take that same problem, but take more of a graphical approach to it to make it look a little bit more obvious. So we have function of x equals x plus 2 over x minus 3. Get out our little, oops. There we go. Took a minute for it to show up. All right. So when we evaluated the limit, let's see, we were looking for the limit. Oops, my draw pen. My limit as x approaches 3. So we were taking a couple of values. Let's see, one of them we took, we took 2.5 or we took 3.5. But for the sake of this graph, we'll take more whole numbers. So we'll do 2, for example. X equals 2, so we'll get, let's see, function of 2 equals, it would be 4 over -1, so it would be -4. Function of 1, that would be 3 over -2, so it would be -3 halves. Function of 0, that would be -2 thirds. Okay, yeah, that looks right. So then we'll go ahead and do some values greater than 3 to kind of get an idea of what's going on here. So a function of 4, that would be 6 over 1, so it's just 6. Function of 5, so that would be 7 over 2, 7 halves. Function of 6, so that would be 8 over 3. So we'll go ahead and plot some of these points. So x is 2 at -4. Put a little dot right there. Function of 1 would be -3 halves. So it'd be about right here. 0, it would be 2 thirds. So it'd be about right here. Okay, that seems about right. I think 3 points is pretty good to get an idea of what this curve is looking like. Oops. All right. And then we'll take some of our larger values. So x of 4, that would be 6, that would be way up here. X of 5 is 7 halves. Let's see, so somewhere in here. X of 6 would be 8 thirds. It's a little bit closer here. So you'll see that the general curve is like this. Now if we were to, let's see, can we zoom out? Not sure if we can zoom out, but anyway, if you were to zoom out, you would see that there actually is what we call an asymptote here at x equals 3. And that corresponds very closely with the limit, because you see when we plot this graph, from the left-hand side, it never touches 3, but it goes to negative infinity. From the right-hand side, it also never touches 3, it goes to positive infinity. So we would say that this limit doesn't exist because the limit on each side is not equal. And the graphical representation of that makes it a lot more obvious. Let's go ahead and go on to another problem real quick. Let's see. So something pretty common that you'll see in algebra and calculus is piecewise functions. And piecewise functions are a point of interest for limits because they go hand in hand with our definition of a limit. So most piecewise functions, maybe one of the most common ones is just absolute value function. So that always is going to be a piecewise function because you would say that, when x is positive, it's going to be equal to x. So if the function of x is the absolute value of x, you'd say the absolute value of x equals x when x is greater than or equal to 0. But the absolute value of x actually equals the opposite of x when x is less than 0. Because if you plug in -2 to the function, for example, the absolute value is going to be 2. So the opposite of -2 is 2. And this is actually interesting because from a graphical approach, let's see if we can get a graph up here. There we go. So if you have a function, graphically, that looks something like this, where you have a point, an open interval, oops, it's supposed to be linear. So this is a piecewise function where when x is greater than 0, well, let's go ahead and fill that in actually, yeah. So when x is greater than or equal to 0, oops. So when x is greater than or equal to 0, the function is actually just x. But when x is less than 0, the function it looks like it would be x plus 2. So if we were given this graph when we wanted to find the limit, it actually wouldn't exist because the limit as x approaches 0, at least the limit as x approaches 0 does not exist, because evaluated that from the left-hand side, it would be a different value, it would be 2, whereas from the right-hand side it would be 0. Alright, that's a pretty good review of limits. So we'll go ahead and do a little bit of differentiation. So we'll start with product rule. Probably a great to start is, obviously the definition of derivatives. Let's see. So there's definitely a lot more nuance to differentiation, but some of the more basic differentiation, you'll have something like x squared, and we know that the general rule, if you want to do d over dx, so the derivative of x squared, you would take the exponent and you would bring it down as a factor, and then you would multiply it by the original base, and then you take the power, you subtract 1, and that would be the derivative. So the derivative of x squared is 2x. Now when we go ahead and do product rule, I'll actually show an example. So x squared is pretty obvious. It's probably one of the most obvious examples you can use when describing a derivative. But if you had x times x and you were told you couldn't conjoin these and you couldn't say they're just x squared, you'd actually use a product rule. So we know that these are going to be the answer, but if we use our product rule knowledge, which I guess I should write that, that's kind of important. So it deals with when you have two unknowns that you're multiplying together. So let's say that u and v are functions of x, so the derivative of u times v is the derivative of 1 times the original of the second plus the original of the first times the derivative of the second. So we would have, let's see, so it'd just be u prime times v plus uv prime. I think that's the easiest way to put it. So u prime times v plus uv prime. So in this case, in this example, both our u and our v happen to be equal. So we'll go ahead and, so if we want to convert this to be looking at the same as the product rule, u prime, so our u is x, so u prime, so the derivative of x is 1, and then multiply that by v, which is just x, and then we'll add, well, let's see, u is just x still, and then we'll multiply by the derivative of x, which is 1, and that equals 2x. This is a very simple, straightforward example of how the product rule works, but you can see that you can basically tear apart the definition of the product rule as just a derivative. They're very similar in this case, but I purposely chose a very easy example. So let's go with something a little bit more difficult. So hopefully you know a lot of the trigonometric identities as well as their derivatives. So for example, the derivative of x, a derivative of sine of x equals cosine of x. It's a pretty important derivative to know. And obviously there's also the derivative of cosine of x, which actually equals the opposite of sine of x. So we'll go ahead and use that in an example. So let's say we wanted to find the derivative of the product of these two. So sine x times cosine x. So again, we want to use our u prime v plus uv prime. Now we'll just lay it all out there so it's very obvious. U we'll choose to be sine of x just because it's the first factor. So we'll say u prime equals cosine of x. And then we'll go ahead and, let's see, v is cosine of x. So v prime is negative sine of x. Now if we plug everything in, it's very straightforward. So I think a pretty good way to look at this visually. You have u and u prime, you have v and v prime. It's kind of like a cross multiplication almost. So you take those terms and those terms, and you get u v prime plus u prime v. So in this case it would be, let's see, u prime is cosine, v is cosine, so this would actually be cosine squared of x, and then you would add, let's see, so we'd have sine of x. Yeah, we have sine of x and we multiply by negative sine of x, so it would be plus a negative sine squared of x. So we see that this is actually our answer. The derivative of sine x cosine x is cosine squared x minus sine squared x. All right. So So we'll move on from there to the quotient rule. Let's see. Quotient rule. All right. So the quotient rule states if you have a function u over v, where u and v are functions of x, the derivative, so let's put d over dx is equal to, get out of here, there we go. So the derivative is equal to v u prime minus u v prime over v squared. And the way I learned this was always low d high, so low being v, high being u, be low d high minus high d low over low low. So if you write that out as words, you know, low is L, high is H. You can just remember LDH minus HDL over LL. So low D high minus high D low over low low. LDH minus HDL over LL. All right, we'll do a straightforward example with this one as well. Let's see. So example, we have a function of x equals 2x squared over x cubed. So again, I think it's pretty helpful to just lay out our u prime, our v, and v prime. So u is our high, which is 2x squared. U prime is the derivative of u, so that would just be 4x. All right, now we'll go ahead and go into v. V is x cubed, which means our v prime is 3x squared. Now we can just plug all of this into our algorithm for figuring out the derivative of a quotient. So low d high, which would be v u prime. So we have v, which is x cubed, times u prime, which is x to the fourth, I'm sorry, 4x. And then we subtract u v prime, which is 2x squared times v prime, which is 3x squared. And that's all divided by v squared, which is x to the 6th in this case. So we'll go ahead and do some arithmetic, simplify everything out. We get 4x to the 4th minus 6x to the 4th over x to the 6th. All right, and then those share bases, so we'll go ahead and do negative 2x to the 4th over x to the 6th, which is negative 2x to the negative 2nd. So the derivative of 2x squared over x cubed is negative 2x to the negative 2nd. All right. Something you'll do a lot in Calc 1 especially, actually all throughout calculus. If you continue on, you'll use a lot of trigonometric functions and you'll use their derivatives, and it's very important stuff. So the next example, we'll go ahead and do an example of a trigonometric function. So let's say we need to find the derivative of sine x over cosine x. So if you're real smart, you recognize this as tangent x. But we want to actually use this use this with the quotient rule to actually find the derivative of tangent x. So again, we set out our u's and our v's. So u is sine x. We have u prime is cosine x. It's important. V is cosine x. V prime is negative sine x. And then we'll go ahead and plug that into our low d high minus high d low over low low. And we get, let's see, so low d high, so that'd be cosine of x, times the derivative of sine of x, which is cosine of x. We subtract, so that was v, no, that was v times u prime. So now we want v prime times u, which is negative sine x times sine x, and that's all over low low, which is cosine squared x. Correct? Yes. And we'll go ahead and simplify this out. We actually get, is that correct? Yes, it is. So we get cosine squared x plus sine squared x over cosine squared x. Something you'll notice, or something that's actually a very important identity, is cosine squared of x plus sine squared of x is equal to 1. So this would be 1 over cosine squared of x, which by another trigonometric identity, that's actually equal to the secant squared of x. So we have found that the derivative of sine of x over cosine of x is secant squared x, and this is equal to tangent of x. So we've just found the derivative of tangent of x. All right. This is a great time to go ahead and do some example problems, and as always, if there's anyone in the audience who wants to ask a question, go for it. I'm watching, waiting for you, but otherwise I'll just go ahead and work on some problems on my own. You can follow along and hopefully learn something out of it. Alright, so let's do a couple examples involving limits, where we need to do a couple of little algebraic processes to actually figure out a limit. Alright, so let's say we have a function x is equal to x plus 5 squared minus 25 over x. So let's say we want to evaluate the limit as x approaches 0 of our function. So if we just were to straight up evaluate x at 0, you'd see that we have an x in the denominator, and division by 0 is undefined. So we wouldn't really be able to find the limit that way. So what we'll have to do is we'll have to just do some algebra to figure out what the limit here is. So we'll go ahead and FOIL out x plus 5 squared. So we would get x squared plus 10x plus 25. So that's that term, the term with the squared, and we don't want to forget that minus 25. It's very important. And then we put that all over x still. So we do a little bit of simplification. So the limit as x approaches 0. And this is, so the 25's cancel out, so we have x squared plus 10x over x, and you'll see that in the numerator we have a factor of x in each of our terms, so we'll go ahead and redistribute that out. So we have the limit as x approaches 0 of x times x plus 10 over x, and then these x's actually cancel out. So we're just left with the limit as x approaches 0 of x plus 10. And we can obviously evaluate that at x equal to 0. So we would just say that the limit as x approaches 0 for f of x is 10. All right. Let's do a little bit more complicated example. So let's say we have a function that involves absolute value. So we have a function x, f of x. Come on. There we go. That's an f now. Function of x equals x plus 1 over the absolute value of x plus 1. So as we saw in our graphical analysis or graphical approach of limits, usually when you have an absolute value in a function, that means it'll be a piecewise function. So there's a certain point where it goes from being positive to negative, where it's discontinuous, you would say. That's important, definitely important for limits, also important for derivatives, as you'll find out as you learn about differentiation a little bit more. So let's just set up our knowledge of absolute values, or our definition. So x plus 1, the absolute value of that, it's equal to x plus 1 as long as x is greater than or equal to negative 1. Because if it were any less than that, then this x plus 1 expression would be less than 0. And the absolute value of x plus 1 actually equals the opposite of x plus 1 whenever x is less than negative 1, because that expression would be negative, so the absolute value would still be positive. So we want to add in that little minus to account for the discrepancy. All right. So here we'll definitely need to go back to finding limits from the left or the right side of a function. So I guess it's important to mention we're interested in the limit as x approaches negative 1. So if we evaluate negative 1, we get a 0 in the denominator. We can't do that. So we'll go ahead and let's start from the positive side. So we're concerned with this first part of the piecewise function. So x plus 1, the absolute value of x plus 1 is equal to x plus 1 whenever we're finding a limit greater than negative 1. So we'll go ahead and just take our function pretty much at face value, plug in x plus 1 in place of the absolute value of x plus 1. You should get x plus 1 over x plus 1, which, the limit as x approaches negative 1 from the positive side, that is equal to 1, because anything over itself is going to be 1. But now let's go ahead and look at the limit as it approaches negative 1 from the left-hand side, or from values less than negative 1. So we can go ahead and go back to our definition for absolute value for this as well. Say that the absolute value of x plus 1 is equal to the opposite of x plus 1, in the case that x is less than negative 1. So we'll go ahead and put x plus 1 over the opposite of x plus 1. Pretty straightforward. Limit as x approaches negative 1 from the left-hand side is going to be negative 1, because we have that extra minus sign. So remember, very important, the definition for limits, if it's not the same from the left-hand side as it is from the right-hand side, that limit actually does not exist. So we found the limit from the right-hand side, we found the limit from the left-hand side, and they do not match. They are not equal. So if you have this function, and we want the limit as x approaches negative 1, limit as x approaches negative 1 actually does not exist. All right. Let's do a little bit more complicated issue with limits, or I'm sorry, a little more complicated exercise, not issue. We love exercises. Let's see. So we have our function of x is equal to square root of x squared plus 4x, and then we want to, let's see, subtract 2 times root 3, and it's all divided by x minus 2, and we want to find the limit of f of x as x approaches 2. So again, we just evaluate this straight at 2. You get 0 in the denominator. We can't do that, so we need to do a little bit of algebra here. So one very important thing from some later algebra classes you learned is that whenever you have two terms minus each other, and you want to make it a little bit more complicated, more fancy, what you actually want to do is you want to multiply by, so if you have a minus b, you want to multiply by a plus b, and you'll find that you can take the multiplication of two binomials, you actually get just a sum of two squares. So we can both eliminate the square roots in each of the terms up here, and hopefully we'll get something we can use. So we'll go ahead and just do that straight away. So we'll multiply this by x squared plus 4x plus 2 root 3 over, and then we have to multiply by 1. It has to be 1, but in the form of our choosing. So we'll get all this junk stuck in the denominator, but it'll help us a lot in the numerator. So we multiply that out. Again, we'll skip a few steps here. We'll basically get this first term, which we can call a, and the second term b. And we'll basically get x squared minus b. So this will give us x squared plus 4x minus, so this is actually just root 12. So this will be minus 12 over x minus 2. Oh wait, no, that's I'm missing something pretty big. We have to multiply this whole thing out in the denominator. So we'll get x minus 2 times this whole denominator up here. We'll come back to that. Right now we're focused on the numerator. We want to try and get this x minus 2 out of the denominator so that we can evaluate at 2. So in the numerator we want to see if we can pull out an x minus 2. So let's assume we can take this out as a multiplication of binomials. So the only way to, you'd have to reverse FOIL this, and then the only thing times, so we want to find something times 2 that equals 12, which is 6. So we put 6 over here, and then, well, this has to be x. So x times x is x squared, x times 6 is 6x, or is it negative 6x? That's what we want to find out. And in this case, we get plus, because we want that to cancel out to a positive 4x. So that's our numerator. Our denominator is x minus 2 times this whole thing, root of x squared plus 4x plus, we'll just put this as root 12 for now. So as you see, x minus 2's, they cancel out. And that's really the crux of this problem, is we get that x minus 2 out of the equation. And we're just left with function of x equals x plus 6 over root of x squared plus 4x plus root 12. Alright, and then we just can evaluate our limit at 2 now. So evaluate x plus 6 as x is 2, we get 8 over, and then we get square root of 4 plus 16 plus root 12. Just do some simplification. Is that right? I don't know, this is supposed to be an 8. So it should be root 4 plus 8. Yeah. So we get x plus 2 root 12 equals 8 over root 48, which equals 8 root 48. We just want to rationalize our denominator. And that simplifies to root 48 over 6. All right, so the limit of this whole function up here, we evaluate at 2 with little algebraic tricks, and we get root 48 over 6. All right, so those are a couple a little bit more in detailed exercises involving limits. So we'll go ahead and go back and do some product rule practice. So let's say we have a function, so f of x equals 6x cubed minus x times 10 minus 20x. Okay. So obviously we could just FOIL this out, but we really want to get some practice with the product rule. And when you're actually using the product rule, there's going to be a lot of times where you just can't, multiply it out and just take a bunch of derivatives. For example, when you're working with trigonometric functions, as we saw in our example of, sine x, if we had sine x times cosine of x, you can't really just, simplify it to just a term. It's always going to be a product, whereas this we could FOIL it out and just get a bunch of terms that we could take derivatives of. But we want to do the product rule because that's fun. All right, so we have our u, in this case, 6x cubed minus x. Our u prime, so we do the derivative of 6x cubed. We get 18x squared minus the derivative of x, which is just 1. Then we have our v, which is 10 minus 20x. We have our v prime. So the derivative of a constant is 0. Derivative of 20x is just 20. So our v prime is actually just, v prime equals negative 20. All right, so we plug that into our product rule, which I'll write it up again. U v prime, the derivative of u times v, I should denote. So d over dx of u times v equals u v prime plus u prime v. All right, so we'll scroll down a little bit here and we'll plug everything in. So we get, let's see, which way did I write it? So u v prime, so u, which is 6x cubed minus x, times v prime, which is negative 20. And we want to add u prime v. Am I doing this backwards? No, I'm not. Okay. So u prime is 18x squared minus 1. And our v is 10 minus 20x. So we'll still have to do some FOILing in this problem anyway, but hey, I mean, let's practice with the product rule. Let's see, so we'll distribute this minus 20, so we'll get negative 180x cubed. We'll get a plus 20x. That's our first term. We'll add, let's see, this is 180x squared minus 360x cubed minus 10 plus 20x. Do a little bit of an algebraic simplification, or arithmetic simplification, I guess you could call it. And we get, let's see, no, this is 120. It's not 1. Yeah, I was mixing that up. Okay, so yeah, so this is 120x cubed. So we add this all together, we get negative 480 x cubed. I'm just collecting like terms and put our terms in descending order in terms of the power of x. So we'll put our x cubed first, plus 180 x squared. We have two 20x's, so that'd be 40x and minus 10. Alright, so the derivative of this whole function is negative 480 x cubed plus 180 x squared plus 40x minus 10. All right. I think that's a pretty good stopping point. We covered quite a bit: limits, product rule, quotient rule. So we'll go ahead and stop it there.